Hi students. In this lecture, I am going to discuss questions from H.C. Verma. Let us see first one. Let's see the question given. A circular loop of radius say carrying a current I is placed in a two-dimensional magnetic field. The center of the loop coincides with the center of the field. The strength of the field at the periphery of the loop is B. Find the magnetic force on the wire. Let us see how to start. So first of all, make the given diagram. So it is given a circular loop carrying current. It is a circular loop carrying a current and a current direction given anti-clockwise. It is anti-clockwise. And coming to direction of the field, it is confined to plane and radially outwards. You can see here B like this and here B like this. It is radially outwards confined to a plane. And given one more thing, strength of the field at the periphery of the loop is B. That means at each and every point on the periphery, modulus of B bar is the same, but direction not same. That means field is non-uniform. Okay, that's why even though it is a current loop, net force on that is not zero. Okay, let us see how to calculate. It is given radius equal to A. Right, for example, consider one small part on the periphery because the field is not uniform. I am taking the small part on the periphery. Suppose take here. This is element of length dl. Okay. And I am taking this is xy plane. X, y. Then here direction of current. It is along positive y-axis. Okay. So force acting on this element df bar is equal to I into dl bar. It is a dl into direction. Direction is now along y-axis, right? Current is like this. Current like this means it is now along y-axis at this location. That is dl into j cap cross I into dl bar cross b bar. B bar is now b into direction is along positive x. So it is now I cap. So it is now I into dl into b direction part j cap cross I cap. That is minus k cap. That means on that element by magnetic field force is now into the board, right? Minus k cap. Now let us take one more element of length dl and I am taking diametrically opposite. Now see carefully. Here dl bar direction will be minus j cap because current is now like this. Okay, you can see here current flows. It is given anti-clockwise coming to here. It is along negative y-axis. So it will be minus j cap and coming to field along negative x-axis. This is minus sign. Minus j minus sign. Minus into minus. It is a plus. It is again minus k cap. That means we can conclude that on each and every small part, magnetic force is now into the board. Direction is same. Therefore, net force acting on the loop that is equal to integration of This value I into dl into b. I into dl into b. I and b both are constants. Take outside. Integration of dl. If you take now sum of those elements, dl, again dl, again dl. If you take sum of all these things, we are going to get it is circumference, which is equal to 2 pi r. Okay. This is now I into b into 2 pi r. Here are given r is a. So 2 pi a. That is now net force acting on the loop. Okay. So this is an example for non-uniform magnetic field, right? That's why on the loop net force is not zero, right? Let us see next one. Two metal strips, each of length L, are clamped parallel to each other on a horizontal floor with a separation B between them. A wire of mass M lies on them perpendicularly as shown. A vertically upward magnetic field of strength B exists in the space. The metal strips are smooth, but the coefficient of friction between the wire and the floor is mu. A current I is established when the switch S is closed at the instant t equal to 0. Discuss the motion of the wire after the switch is closed. How far away from the strip will the wire reach? Okay, this is the question given. Let us see how to solve it. First of all, make the given diagram. This is now that wire and rails are like this, and separation between rails, that is given as B, and this is now connected to a battery through a resistor. Through a resistor. This is now switch. Now once the switch is closed, current flows now. It is anti-clockwise. Okay. Current is now anti-clockwise. And we can see field. It is now given normal to plane of the board. It is now outwards. It is given dots, means outwards, means towards us. And you can see here this length is given L. Let us take this arrangement is now in XY plane. This is X and this is Y. Now see what happens when switch is closed. Current flows like this. Since there is a magnetic field, force acts on the current carrying wire. Let us focus on force acting on that direction part. Force F bar equal to I into L bar. Here length is B. Okay. We have to focus now through which part current is flowing. Okay. So only from here to here means this part we have to focus. That is now in the place of L, I'm taking B. Direction part, current is now like this means it is along y-axis. So I'm taking it as B J cap cross I into L bar cross B bar, direction of field. It is normal to plane of this board. It is along positive z axis. It is now B K cap. Okay. Then see what we get. I into B into B. Direction J cap cross K cap. That is I cap. That means magnetic force acting on this wire is right side. Okay. So because of this force, work is done on this wire, right? So until this wire reaches the end of this rails, that force acts. Okay. And once that wire comes on to ground, now there is a frictional force. On reaching ground, now there is a frictional force. And once it reaches the ground, there is no current. Okay. Because it is now on ground. As long as it is on the rails, current flows. Once it reaches ground, there is no current. No current means no magnetic force. Okay. So here see what we have to calculate. Is asking how far away from the strip will the wire reach. That means see initially velocity 0. Finally, after traveling some distance yet, it comes to rest. So final velocity is 0. Initial velocity is 0. Final velocity also 0. That means delta K is 0. So I am taking here work energy theorem. W net is equal to delta K. Delta K 0. As long as it is on the rails, work is done by magnetic force. Okay. And that is now force is I into B into B. Magnetic force, which is a constant, into displacement, that is now L. So into L. So by magnetic force, work done is positive. And once it reaches ground, it is now frictional force. Velocity is now right side, but frictional force is left side. Therefore, by frictional force, negative work is done. So it is minus mu mg into x, that is equal to 0. Now see from this x value, it is I B B L upon mu mg. Okay, like this, we can get the value of x. Or we can solve same thing by using kinematics. That means initially velocity is 0. Calculating velocity when it is about to reach ground. Okay, initial velocity 0. Final velocity we have to calculate. L is displacement. And acceleration will be this force by mass. And using v square minus u square equal to 2as. So finding velocity just before landing on ground. And again, that velocity becomes now for this part, initial velocity. Final velocity is 0. And once again writing v square minus u square equal to 2as. In this case, a value will be mu g because net force is frictional force. So either we can solve by using kinematics or by using work energy theorem, right? Let us see next one. Let's see the question given. A metal wire PQ of mass 10 gram lies at rest on two horizontal metal rails. Separation given. A vertically downward magnetic field of magnitude 0.8 Tesla exists in the space. The resistance to the circuit is slowly decreased, and it is found that when the resistance goes below 20, the wire PQ starts sliding on the rails. Find the coefficient of friction. Okay, let's see how to start. So given these are rails, on those rails there is a wire which can slide There is a wire which can slide. Field is now into the boat, normal to boat, inwards. Now connected to, so by conducting wires, we're connecting to a battery, 6-volt battery. And you can see here, this is now a variable resistor, means we can change resistance, 6-volt battery. So condition given that when resistance goes below 20, see what happens here. Resistance of the circuit is slowly decreased. So when resistance is decreased, current will increase because current equal to 6 by resistance. When R is decreased, current will increase. When current is increased, magnetic force acting on the wire will increase. Magnetic force is I into L bar cross B bar. L bar, it is in the plane of the board. B bar, normal to plane of the board. So between L bar and B bar, angle is 90. Therefore, modulus of the force I into L into B. When this force is able to balance limiting friction, that is a mu mg, then it is about to move or about to slide. So mu mg is a constant, L is a constant, B is a constant. So by decreasing resistance, we can increase the current. When current is increased, this total value will increase. At one point of time, this force is able to balance limiting friction. Then the wire is about to slide. That means here R value 20, about to slide. So substitute that here, then we are going to get coefficient of friction. So mu equal to, it is ILB upon mg. Remaining just a calculation part. So I hope you can do calculation. Let us see next one. A conducting wire of length L lying normal to a magnetic field B moves with a velocity V as shown. Find the average magnetic force on a free electron of that wire. Next given, due to this magnetic force, electrons concentrate at one end, resulting in an electric field inside the wire. The redistribution stops when the electric force on the free electrons balances the magnetic force. Find the electric field developed inside the wire when the redistribution stops. And finally, we have to calculate potential difference developed between the ends of the wire. Okay. See how to start. So first make the given diagram. So velocity is V. Assume that electrons inside are stationary. That means with respect to the wire, electrons are at rest. Okay. Electrons stationary. That means velocity of those electrons will be velocity of this wire. Right. And given field is now into the board. Normal to plane of the board, it is inwards. And this length is given L. Length is given L. Field strength is B. Let us consider this board plane as XY plane. And this is our choice. So first we have to find average magnetic force. We have to find average magnetic force on a free electron. So force equal to Q into V bar cross B bar. V bar cross B bar. Charge of electron is negative. Okay. So I'm taking here minus. Charge of electron is a Q. V. It is V only. Direction. It is I cap. So V I cap cross B bar. B bar is now into the board. So B into the board means it is minus K cap. Okay. Then see what we get. Minus of minus plus I cap cross K cap. That is minus J cap. So QVB minus J cap. Okay. That is the average magnetic force on a free electron of the wire. So next what we have to calculate. So now he is saying that due to magnetic force, electrons concentrate at one end. You can see here on electrons. Force is now, it is given direction minus J cap. Minus J cap means they are moving now down, right? That means this end becomes negative and this end becomes positive. So because of this accumulation of electrons, electric field is established and direction is from plus to minus, means like this. I'm showing here. Direction of electric field, that is now downwards from plus to minus. And you can see because of electric field, electric force equal to Q into E bar. If charge is negative, force will be opposite to E bar. E bar is downwards, okay, like this means along negative y-axis. Since electron is having negative charge, on electron, electric force will be, it is along positive y-axis, Q into E. Magnetic force is downwards. That is a QVB. Q constant, V constant, B constant. And here Q constant coming to E value. As electrons are keep on accumulating, strength of the field keep on increases. At one point of time, electric force is able to balance magnetic force. Then redistribution of electrons will stop. Okay? That means when these two are balanced, there is no more accumulation of electrons. So I can write here QE is equal to QVB. Modulus values are same, directions opposite. So strength of the electric field is VB. Okay. And this field is uniform. Since the field is uniform, potential difference across the ends, it is equal to E into L. Okay. That is now L into V into B. This is the potential difference across the ends of the rod. Okay. Let us see the next problem. Let's see the question given. A square coil of HL having n turns carries a current I. It is kept on a smooth horizontal plate. A uniform magnetic field B exists in a direction parallel to an edge. The total mass of the coil is M. What should be the minimum value of B for which the coil will start tipping over? Means it is about to rotate. Okay. Let us see how to start. It is given a square coil. Consider this board plane as a horizontal plane. So we are taking the board plane as a horizontal plane. That means we are seeing from the top. Okay. We are seeing from the top. and C given having n turns. Side length is L, n turns. Strength of the field, that is given B. Next, its mass, capital M. So we have to calculate a minimum value of B. See how to start. So coming to here, this is in a horizontal plane. We are seeing from the top. In such a case, gravitational force downwards, normal reaction upwards, both are balanced, right? And you can see direction of the magnetic field. It is a parallel to an edge. That means B bar is now either like this or like this. Okay. Now see what happens. For example, current is now, let us take anti-clockwise. It is a completely our choice. See what happens here. It is anti-clockwise. Now, suppose this is a P, Q, R, S. On PQ, no force because of magnetic field. The relation is that between L bar and B bar angle is 0. Okay. So force equal to I into L bar cross B bar. Right. So on PQ, L bar along, I can say this is X and this is Y. Direction of L bar is I cap. B bar also I cap. That's why on PQ no force acting. On SR again no force acting because angle is 180. Remaining is now PS and QR, right? Coming to on SP, see direction of force. Let me write here on SP. I into direction of L bar, that is minus J cap, L into minus J cap, L into minus J cap. Okay, current is along negative y axis. B bar, it is along x axis. So B into along x axis, it is I cap. So force is now ILB direction part. J cap cross I cap, that is minus K cap. Having here minus, it is a K cap. So force acting on this, it is towards us. Okay, towards us. And force acting on this, it will be into the board, right? That means this is now having a tendency of rotation about QR. I am repeating on SP, cross check once, minus J and I. J cap cross I cap. So we have learned I, J, K. I cross J, K. This is J cross I minus K. Minus of minus plus K cap. So force on this is outwards and on this will be inwards. So loop is having a tendency of rotation about RQ. Getting the point. Now, if this torque is, if it is able to balance a torque due to gravitational force. See here what we can write. It is a square loop. Force is now I into L into B. Rotation about this axis. So into L, this is a torque. If this is greater than or equal to torque due to gravitational force, mg into L by 2, then it will topple. Equal to means about to topple. Greater than means it will tip. Okay, it will tip over the edge. That's the calculation part. So L gets cancelled. It is now B minimum, or I can say B greater than or equal to mg upon 2IL. mg upon 2IL. So when they ask minimum, So that minimum value is, it is equal to mg by 2il. Means when it is equal to this value, it is about to tip about this edge. Greater than, it will tip about this edge. Okay.